Hey, this is Horner, and we're going to take a look at circuits, and mainly we're going to do some VIRP charts. But before we do that, let's just look really at some basic series and parallel setups for resistors. So on your equation sheet, you're going to notice that they will say the resistance in series is equal to the sum of some sort of number, so I for integer, of all the resistances, all the resistors that you would have in a specified series setup. So I like the equation better. RS is equal to R1 plus R2 plus R3. I think that works better. So we'll do these 12 plus 4 plus 6. And 6 and 4 is 10 plus 12 would be 22. And then remember the unit is the ohm. For number 2, this one is in parallel. And so on your equation sheet, they're going to say that 1 over the resistance in parallel is equal to the sum of an integer number of resistors where you have 1 over Ri. I like to do this one a little bit different also. I just say resistance in parallel. 1 over the resistance in parallel is equal to 1 over the first plus 1 over the second plus 1 over the third, and on and on. I always call this one add inverse and flip, F-L-I-P. So I'll show you why we do that. We have 1 over the parallel resistance is equal to 1 over 12 plus 1 over 4 plus 1 over 6. Now our common denominator here is going to be 12. So this is going to be 3 over 12. This one is going to be 2 over 12. 3 plus 2 is 5, plus 1 is 6, so this is equal to 6 over 12. So your resistance in parallel is not 1/2. We have to remember to flip it. So now if I flip this, it's going to be 12 over 6, and that will give me a resistance of 2 ohms. So the resistance here in parallel, you'll notice, is very small. It's smaller than the smallest resistor, and the resistance in series for the same 3 resistors is actually bigger than the largest resistor. So that's the important thing with that. All right, so let's go ahead and take a look at a series circuit. So this is a good series circuit. Pretty easy one to do. In series, there's certain things that we have to remember. And the first thing that we have to remember in series circuits is that the voltage in this one adds. And it adds because of the loop rule. So remember, if this is 10 volts, then these each have a resistance that should be less than 10. And when you add them together, they should end up being 10. And the loop rule says that all the voltages should add up to 0. So if you make this one negative 10, and then you can have positive values for these, when you're done, the whole thing should equal 0. On the other hand, the current in this one, so current is the same for each resistor. So whatever my current is going into this branch should be the same as coming out. The current going into this branch then should be the same as what comes out of it. And then same thing here to here. So this is actually the junction rule, is what we have to remember for the AP test. So let's go ahead and do this series circuit. We can go ahead and figure out what the different variables are. So to do that, we're going to use something called a VIRP chart. So this is voltage, current, resistance, and power. And some people like to put a star here because voltage is equal to current times resistance. Power is something that we're going to look at here in a little while. So we actually do want to make an actual table out of this. And the first thing you always want to do is, if it's just a simple series circuit, we're just going to put our 3 resistors in, then we're going to draw a line, and we're going to call this row the equivalent. Whoops. We're going to call this row the equivalent row. So we're just going to put EQ on the equivalent row. So here we've got 15 plus 10 plus 6, and that should be equal to 31, so that was pretty easy. Over on this side, we're going to have 10 volts. So you'll notice that the very bottom line is going to just tell you what those different things are, and you'll see that they are adding up to about that 10 volt that you need. So 10 volts there, we have 31 ohms for resistance, and now we need to figure out what is the current. And in order to find the current, we're going to have to use Ohm's law. So on your equation sheet, Ohm's law has this form. It says I is equal to V over R, which for us works out really well. So now we're just going to take 10, and we're going to divide 10 divided by 31, and you should end up with 0.3226. So our current is 0.3226. So that would be the current in this wire right here. When I get to each one of my resistors, I notice that we said that the current is the same because of the junction rule. So when I go to the 15 ohm resistor, the current going in is 0.3226, so the current going into the resistor is also 0.3226. So this one's 0.3226, this one's 0.3226, and this one is 0.3226. So current's the same, so we can just list those. The next thing we need to do is go through and find out what is the voltage for each one. So we said voltage is current times resistance. We're going to take 15 times the 0.3226, and we're going to end up with 4.84 volts. We're going to take the 0.3226 times 10, and we're going to end up with 3.226. Oops, 3.226. And then finally, we're going to take 6 times 0.3226. And here we end up with 1.936. If you add these up, they should come up very, very close to 10, which they do. And now to find power. So for power on your equation sheet is equal to IV. But because I is equal to V over R, if I plug V over R in right here, I'm going to have V squared over R. And then for the last power equation, I just remember that V is also equal to IR. That's a normal form of Ohm's law. And if I plug that in for V right here, I see I get I squared times R. So any of these three equations will work. I usually just like to use I times V. So we're going to take 4.84 and we're going to multiply that times 0.3226, and we end up with an answer of 1.56. And remember, the unit here is watts, here is ohms, here is amps, and V is volts. So that's 1.56. The next one is 3.226 times 0.3226, and you end up with 1.04. The next one is 1.936 times 0.3226, and you end up with 0.625. If I take 10 times 0.3226, I end up with 3.226, and if I add these up, I should get a number that's very close to that. And at this point, we're done with this series circuit and finding out everything we need to know using the VIRP chart. The reason I like to use the VIRP chart is they might ask you initially, what is the power in this 10 ohm resistor? And you would have to go in and add all your resistances up, get this number, find out what the current is, and then go back up. You could just plug this number in and then multiply I squared times R to find out what the power is. You wouldn't have to do everything else. The College Board will only grade what you show them, so they will not grade this because this is not showing them how you did it. I know it seems like it is, but they want to see everything step by step. So we'll go through how to do that later. Let's go ahead and take a look at the next one. So our next circuit is called a parallel circuit. This circuit is a parallel circuit. You can see it looks like a ladder here. These are all parallel with each other. And so we do know that this is a parallel circuit. In parallel circuits, we know that the voltage is the same for each one of the resistors, and that's because of the loop rule. So remember, here we've got one loop going through the 6 ohm. We've got another loop, we'll make it yellow, going through the 10 ohm. And then finally, we'll do one more green one here. And this is the last loop going through the 15 ohm. So each one of these should have the same resistance. The same voltage, not resistance. They all have different resistances. The current for each one should add. So current here will add, and that's because of the junction rule, so I'm going to just abbreviate it. You should not, make sure you write it out. But at this junction right here, you'll notice that whatever the current is here needs to be the sum of the 3 here. So that's why the current adds, and that's due to the junction rule. So let's go ahead and do our VIRP chart, V, I, R, and P, and we need to go through and set this up. So here we go. I've got a current of 15, a resistance of 15, a resistance of 10, and a resistance of 6. Now when you add these, remember we have to do 1 over 15 plus 1 over 10 plus 1 over 6, and that's equal to 1 over the resistance in parallel. Common denominator here has got to be 30, so this is going to be 2 over 30. This one's going to be 3 over 30, and this last one is going to be 5 over 30. So 5 plus 3 is 8, plus 2 is 10, so that'd be 10 over 30. Got to remember to flip it, so resistance in parallel should be equal to 3 ohms, and that's what we'll put right here. Our voltage in this circuit is 12 volts, so finding current's really easy. Remember, current is equal to V over R. It's on your equation sheet, so 12 divided by 3 is 4. We cannot put current in here because these are not in series, they're in parallel. We did say the voltage is the same though due to the loop rule, so this is 12, 12, and 12. And now if I want to find the current for each one of these, I'm going to have to divide my voltage by my resistance. So 12 divided by 6 gives me 2, 12 divided by 10 is 1.2, and then finally 12 divided by 15 gives me 0.8. Remember the current should add, so when I add these numbers, yep, they do end up being 4. For power, I'm going to take 12 times 0.8, because P is equal to VI, or IV. I get 9.6 watts here. 12 times 1.2 for the next one is 14.4. And then the last one here is 24. When I add these up, it should equal 12 times 4, which is 48. And if you add them, you'll notice that is what you get, is 48 watts. So that one was pretty simple to do. Let's go ahead and take a look at one more. This next one is what we call a combination circuit. This one actually has both a parallel and it has a series branch. So let's go through and take a look at our VIRP chart for this one. So we're going to do V, I, R, and P. The first thing that stands out is there is a parallel branch. So let's take care of that parallel branch first. So to figure out what the overall resistance in the parallel branch is, I'm going to take 15 and I'm going to add it to 10. Now what I like to do on this chart is I like to make another row here, and I'm going to call this the parallel row. So whatever this ends up being, I will put all the values in this area. Okay, so here we go. We're going to do 1 over 15 plus 1 over 10, and that's equal to 1 over the resistance in parallel. Common denominator here would be 30, so this would be 2 over 30 plus, and then I'm going to do 3 over 30. That's equal to 1 over the resistance in parallel, so the resistance in parallel should be equal to, this is 5 on the top and 30 on the bottom, so I flip it. And so this would be 30 over 5, which is 6. So in this parallel section right here, I know that my overall, I'm going to cross these off just lightly so I can still read them later. I know that this thing acts like a 6 ohm resistor. So I'm going to put a 6 there. Now this one and this one are now in series, so I'm going to put another 6 down for this resistor, so that's what this 6 is. And because they're in series, I just add them together, so that one is going to be 12 ohms. Our overall voltage in this circuit is 32, and if I want the current, I just take 32 and divide by 12, and I end up with 2.667. Now remember, this is in series and this whole thing is in series. So I'm going to go ahead and put in 2.667 since current in series is the same. I'm going to do it here also, 2.667. To find the voltage drop across both branches, I'm going to take 2.667 and multiply times 6, and I get 16.002, so I'm going to go ahead and round this one to 16, same thing here. If I add the two together, my voltage is 32, which is great because in series the voltage adds, current's the same. Now I'm going to start looking at this 15 and the 10. I know that the voltage in each one of these needs to be the same. So they're both going to be 16 because I said in parallel everything has a voltage of 16. The current then is just going to be 16 divided by 15. So I get 1.067, and then 16 divided by 10 is 1.6. So when I add the 1.067 and the 1.6, I do get 2.667. For my power, I'm going to multiply my V times my I for each one. So 16 times 1.067 gives me 17.072 watts. 16 times 1.6 gives me 25.6. 16 times 2.667 gives me 42.672. And I'll notice that if I add these two numbers together, I get this one. So the power in the parallel branch, I just add the two, and that number and the multiplication of the product of these two should be the same, which it is. This one also happens to be 42.672, and then 32 times 2.667 is equal to 85.344. 85.344, and you'll notice that if I add the two things here, which were in series, I end up with 85.344. And that is how to do simple resistors, adding them in both series and parallel. I also showed you how to do a simple series circuit, a simple parallel circuit, and then how to do a VIRP chart for a more complex circuit.